Good evening to all of you. In this video, we wish to study rolling of a body on a horizontal surface. Let us consider a cycle. We are going to ride it in a slightly different way. We are going to hold the brakes tightly and move ahead. What will happen to the wheels? The wheels will not rotate. They will simply translate. This is what we call as pure translation. All points on the cycle will have the same velocity v. Now supposing we lift the rear wheel upwards and turn the pedal. The rear wheel will rotate but not translate. That is a case of pure rotation. Now if you take the cycle normally, you would find that it rolls. This rolling is a combination of translation and rotation. Let us see this in more detail. Supposing we had the cycle wheel translating, if the center of mass were moving at v, every point on the rim, I am showing only 4 points, would move with the velocity v. When it was in pure rotation, if the angular velocity is omega and the radius of the wheel is r, then with respect to the center of mass of the wheel, there will be a tangential velocity omega r at every point on the rim. Yes? Now when we superimpose both these, let us say we have the wheel here. The velocity of this point, tangential velocity is omega r with respect to the center. Here it will be an omega r. I am showing only 4 points, omega r and omega r. All this is with respect to the center of mass. The center of mass is translating at omega. So superimpose that on it. So add v here, v here, v here and v here. So that will give us the absolute velocities of the points on the rim, that is with respect to the ground frame. Now, so the absolute velocity will be the vector sum of omega r and v. Now, we are concerned mainly with the point of contact, with the instantaneous point of contact. That is because frictional force acts at the point of contact. Now we know the role of friction. The role of friction is to prevent slipping. What do we mean by slipping? When you have two surfaces in contact, let us say I put both my palms together and move this way, there is no slipping because the velocity of both the palms are the same. But if I did this, there is slipping. So, when the velocities of two surfaces are different, we say there is slipping between the two surfaces. Now, when we say friction prevents slipping or tries to prevent slipping, what friction is trying to achieve is to make the velocities of the two surfaces in contact the same. So, now let us come back to the situation where the bottommost point, the instantaneous point of contact of the circular shaped body has a resultant velocity which is the vector sum of v and omega r. Three cases would arise. V could be greater than omega r. If v is greater than omega r, the net velocity of the instantaneous point of contact would be towards the right. You would say that the point of contact is slipping towards the right. Now friction, to prevent slipping, will act towards the left. So this was a case of rolling with a forward slip. Now it could also be that omega r is greater than v. Then we say the rolling is with a backward slip. If that happens, friction will act towards the right. And if v equals omega r, then the point of contact is at rest and the horizontal floor is also at rest. And hence there is no slip. So this is what we term as rolling without slipping or pure rolling. When pure rolling, if it is pure rolling, friction will not act. Of course, in all these three cases, we are assuming that no other external force acts on the wheel and only frictional force comes into play. Now what we are interested in is, if there is no pure rolling, obviously friction is going to act, and we are interested in knowing how will this frictional force achieve pure rolling or induce pure rolling. That is our object. Before we do that, one thing we would like to understand is how we study forces for translational effects and how we study torques for rotational effects. Now, when you have a system of particles like a wheel, as we have shown here, to study translation, wherever the forces may be acting, all those forces are brought to the center of mass and the entire body is assumed to be concentrated at the center of mass as a particle. And we study the entire body as a single particle concentrated at the center of mass for studying the translation effect. We apply the Newton's second law. We say F net is equal to ma, where m is the mass of the system of particles and a is the acceleration of the center of mass. To study the rotational effects, we treat the body as a system of particles and the forces will lie at the points at which they are acting, and we will see the torque of these forces about the center of mass. This net torque will be equated to moment of inertia into alpha. Moment of inertia about the axis passing through the center of mass, and alpha is the angular acceleration about the axis passing through the center of mass. So let us take an example. Supposing we have a surface and let's say I have a disk of mass m and radius r. We spin this disk, we give it some angular velocity omega naught and place it on the surface. We are not going to give it any horizontal velocity, linear velocity. We will spin it and leave it here. Supposing this surface is smooth, that is mu is equal to 0. What would happen? If you draw the free body diagram of this disk, there would be mg and there would be n. Since the disk is not moving in the vertical direction, n is going to be equal to mg. Since there is no friction, there is going to be no horizontal force. Because there is no horizontal force, the center of mass of the disk will not advance. So the disk is going to stay at the same place on the surface. What about omega naught? The angular velocity. Is it going to increase or decrease? Let us see. It will increase or decrease if there is a angular acceleration. And angular acceleration is caused by a torque. The torque can be caused only by n or mg. But will it cause a torque? Both n and mg pass through the center of mass. So there is no torque produced by n and mg. Since there is no torque, the angular acceleration is 0 and the body will stay at the same place and continue to rotate at the same omega naught forever and ever. That is an ideal case. Now supposing mu is not 0. Supposing it is a rough surface. See what happens. When you place it, this portion would have an tangential velocity of omega naught into r. So, and the center of mass is at rest. So, this point, instantaneous point of contact, is having a velocity towards the left, or it is slipping towards the left. Since it is slipping towards the left, frictional force will act towards the right. Now, because there is slipping, friction has reached its limiting value. The value of frictional force would have attained the limiting value since there is slipping. So F would be equal to F limiting, that is nothing but mu into N, which is nothing but mu into mg. This frictional force will cause the center of mass to accelerate. So in the horizontal direction, we can write F net is equal to ma, where a is the acceleration of the center of mass. F net is mu mg equal to ma. So the acceleration of the center of mass would be mu g. Now let us see, this frictional force will cause a torque about the center of mass because it is not passing through the center of mass, unlike N and mg. So the torque would be in the anti-clockwise sense, opposite to the direction of omega naught. Omega naught is clockwise, and the torque of F would be in the anti-clockwise sense. So there will be a retarding angular acceleration. So omega naught will decrease. So let us see what that torque is. We have net torque is equal to ICM into alpha. Net torque would be F into R. ICM would be mr squared by 2 small m, mr squared, this would be mr squared by 2 into alpha. F is mu mg into R, that is mr squared by 2 into alpha. M cancels, this is small m cancels, 1 r cancels, and you have 2 mu g equal to alpha r. So we know the angular acceleration, or alpha r is the tangential acceleration. We know the tangential acceleration. Now alpha is the angular acceleration. Now let us see the what happens to the disk. The disk, which was initially at rest, will now start moving and start gaining velocity with a due to the acceleration mu g. The omega naught is going to decrease to some omega. So let us see the point of contact. You will have omega r towards the left and superimpose the velocity of the center of mass. You will have v like this. So v is continuously increasing and omega is decreasing. So omega r is continuously decreasing from omega naught, and there will come a situation where omega r and v become equal and there will be pure rolling. When that pure rolling occurs, frictional force will disappear. So we wish to find out at what time after releasing the disk will pure rolling occur. So we will use the kinematic equations for the center of mass. V is equal to u plus at for the center of mass. So this would be, V would be u 0, initially center of mass is at rest. A is mu g into t. We can also apply the kinematic equations for circular motion. That is nothing but omega is equal to omega naught plus alpha t. So omega would be omega naught plus, now as we said, it is a retarding angular acceleration. So it will be minus alpha into t. So this will be omega naught minus alpha into t. So alpha is nothing but 2 mu g by r into t. So if you multiply it by r throughout, you would have omega r is equal to omega naught r minus 2 mu g into t. Now the situation comes where v becomes equal to omega r. So let us equate these two. If you equate these two, you will get mu gt. This is the mu gt, that is v, that will be equal to omega naught r minus 2 mu g t. If you simplify this, you will get t is equal to omega naught r by 3 mu g. That is the time in which pure rolling will start. When that pure rolling starts, we can get what will be the velocity of the disk. How can we get that? Use the first kinematic equation. Use this. We know V is equal to mu gt. This will be mu g. T was omega naught r by 3 mu g. So mu g cancels and you have omega naught r by 3. That will be the velocity once pure rolling starts. After that, this velocity will remain constant. Similarly, the omega that will be attained is V by R, which is nothing but omega naught by 3. V by R will be omega naught by 3. So the disk will now move at omega naught r by 3 and rotate at omega naught by 3 forever and ever. That is the ideal situation. Okay. Now let us take another example wherein we don't rotate the disk but we give a translational velocity. We give it a translational velocity. That is what we are going to do is keep the disk on the surface and give a short duration impulse, an impulse to the, so we will place the disk here like that on the surface and give an impulse so that it attains a velocity v0. This is a hit we are going to give so that it attains a velocity v0. Of course, that hit should be such that the impulse passes through the center of the disk. Only then it will translate. Otherwise, it will have a, if it is slightly above or below, there would be a rotational effect also. For example, if you had a rod and this is the center of mass of the rod, if I apply a force which passes through the center of mass, the rod will only translate, it will not rotate. For it to rotate, the forces must be off center, either above or below. Only these forces can rotate. So let us say we don't rotate it, we give an impulse of that the linear velocity is v0. Let us again assume that mu is 0. If mu is 0, then what we are going to find is that there will be no frictional force, so there is no horizontal force, and so v0 will remain as it is. And since there is no frictional force, there is going to be no torque. Because there is no torque, there will be no angular acceleration and hence the body will not rotate. So it will continue forever with the same speed v0. But now supposing the coefficient of friction is not 0. Now if you see the bottommost point, the bottommost point will have velocity v0. The disk is not rotating, so there will be no tangential velocity which we put here. So there will be only v0. The slipping is towards the right. So frictional force will act towards the left. But because the slipping friction would have attained its limiting value, and so F will be equal to F limiting, that is equal to mu g, mu mg. Now this frictional force will rotate the disc. This frictional force will have a rotational effect, and this frictional force will retard the body and the center of mass velocity will decrease. So now if you see, you will have omega r like this and v like this. V is continuously decreasing from v naught and omega is increasing from 0. So there will come a time when omega r becomes equal to v, and then there will be pure rolling, friction will disappear. Okay. So let us see at what time this happens. Now again we will use the kinematic equations. V is equal to v naught, v is equal to u plus at. Here now the acceleration mu g of the center of mass is now actually a deceleration. So you have v naught minus mu g into t. Omega would be 0. Initially the angular velocity was 0, plus now it will be an accelerating angular acceleration. It won't be a retardation. So omega naught plus alpha into t. Alpha is nothing but 2 mu g by r into t. So if you multiply this by r, omega r will be 2 mu g t. So there comes the situation when v becomes equal to omega r. So if you simplify that, you get v naught minus mu gt equals 2 mu gt. So that gives us t is equal to v naught by 3 mu g. That will be the time at which pure rolling starts and frictional force will disappear. Now let us see what is that velocity at which pure rolling starts. Use this equation. If you use this equation, v is equal to v naught minus mu g into t. T is v naught by 3 mu g. So mu g would cancel and you will have v naught minus v naught by 3, that is 2 v naught by 3. What will be omega? Omega is v by r, so it will be 2 v naught by 3r. You can get it from this equation also. T is 2 mu g, T is v naught by 3 mu g. So if you put T as v naught by 3 mu g, you will get 2 v naught by 3r. 2 v naught by 3r. Let us now take another interesting situation wherein the surface on which the disc is being placed is not at rest but it is moving. Let us say it is a conveyor belt. Let us say it is some conveyor belt and you place the disc, you give a horizontal velocity to the disc on the conveyor belt. Let's take a situation where there is a belt and this belt is moving at, let us say, v naught by 2, and you place the disc here and give it some velocity v naught. If you did this, see the bottommost point is again going to be moving at v naught, so it is slipping to the right. You see the difference in the velocities, v naught minus v naught by 2 is towards the right. So frictional force will act towards the left. So again the center of mass will be retarded, its velocity will decrease, this frictional force will cause a torque and there will be an omega, and there will come a time when omega is equal to Vr. Yes. No, we shouldn't say omega equal to VR. See, the bottommost point, yes, this is where we have to be careful. This is omega R and this is V, where the center of mass is a velocity V. So, this is rotating at omega. The tangential velocity is omega R with respect to the center of mass. Center of mass has a velocity V. Superimpose that. So, you will have omega R and V vectorially getting added. Now, we wouldn't say V minus omega R equal to 0 because the surface which is there is no more at rest. If the surface were at rest, we could say this. We will not say this. The surface now is moving at V0 by 2. So therefore, the point of contact must have a velocity V0 by 2. So we will say V minus omega R is equal to V0 by 2. So again we will apply the kinematic equations. V is equal to V0 minus mu gt and omega is equals initial angular velocity is 0 plus 2 mu g by r into t. So omega r would be 2 mu g into t. So what is V minus omega r? V minus omega r will be V naught minus mu gt minus 2 mu gt, that we are saying should be equal to V naught by 2. That is the condition for pure rolling now. So this would be V naught minus V naught by 2 is V naught by 2. This will be 3 mu gt or t equals V naught by 6 mu g. That is the time at which pure rolling will start on the surface which is not at rest. Let us get what will be the velocities, the linear velocity and the angular velocity when this happens. We will use this equation. V is equal to V naught minus mu g into t. T is V naught by 6 mu g. Mu g cancels. You will get this as 5 V naught by 6. What is omega? Omega is 2 mu g by r into t. T is nothing but V naught by 6 mu g. So this would be mu g cancels and you have V naught by 2 3s are, so V naught by 3r. That will be omega. See the situation. You have the center of mass moving at 5 V naught by 6 and the angular velocity at V naught by 3r. That is omega. So let's see the point of contact. The point of contact will have a tangential velocity omega r given by V naught by 3 and superimpose the velocity of the center of mass on this, which is 5 V naught by 6. So what is the net velocity? 5 V naught by 6 minus V naught by 3, that will be 6 is the LCM, 2, 5 minus 2 is 3, 3 by 6 is 2 V naught by 2. So the point of contact has got a velocity V naught by 2. The belt is also moving at V naught by 2. So there is pure rolling. Yes, and friction will again disappear. Thank you.